Thanks to Dr. Pevtsov for giving this COFFIES seminar, and it's my great honor to introduce him. Dr. Pevtsov is an astronomer at National Solar Observatory. He serves as an NSO Associate Director and the Director of NSO's Integrated Synoptic Program. He studies topology and evolution of solar magnetic fields and their role in solar activity. Dr. Pevtsov's expertise ranges from solar magnetism to solar stellar astrophysics, and including a substantial understanding of the needs of the US space weather community. Let's welcome and thanks to Dr. Pevtsov again, and we can have him start his seminar.
Oh, thank you for this wonderful introduction. And while I'm sharing the screen, let me see. Do you see it in a full presentation mode now, or?
Yes.
Yes.
All right, great. So, NSO is the federally funded research and development center. That's why, NSF wants us to put this, logo and this. My today presentation is about farsight activity, in the sun, and its use in flux transport simulations. The co-authors on this paper are my colleagues from University of Oulu in Finland. And so there are two Virtanians, Eero and Ilpa, and Kalev Ursula is the one. Let me start from saying the obvious thing that the polar magnetic fields are a really critical aspect of solar cycle. And from the Babcock-Leighton morphological model of solar cycle, we see cycle as a transformation from poloidal, toroidal field back to poloidal. And so at the beginning of cycle, we start from very strong polar fields, and then those fields are transformed to toroidal, active regions are formed, and then it's transformed back to poloidal fields at the end of cycle to begin the next cycle. So from that simple description, it's, the strength of the next cycle should be related to the strength of polar fields, and there is a number of studies that show that in fact you can make a prediction of the amplitude of next cycle based on the strength of polar field. Polar field is also important for modeling of solar wind in interplanetary space, and models like WSA and LIL model are really sensitive to the polar field. So the polar field is important, but it's hard to measure because it's there are strong projection effects, and the field is mostly radial there, and so we see very, very weak component towards line of sight. That morphological description that I just presented, let me turn on the laser pointer. That transformation between poloidal and toroidal field is quite clearly seen in a supersynoptic map. So if you take the observations of magnetic field for a number of years and you plot them as function of sign of latitude and time, that's what you will see. You will see the activity in mid-low latitudes, the active regions. And as they decay, you see this surges of decaying flux moving towards the poles and forming the polar fields. And you also can see, just before I go to the next slide, I want to show how that change in evolution of polar field looks like when you look through the, down from the pole. In this case, I'll show polar view derived from SOLAS magnetograms for the period about 2004 through 2017. So it's somewhere from here in the South Pole to, change in polarity of polar field, and then reversing polarity, and then building up the polar field of opposite sign. So the movie will be here, and it's very, well, let me do it like this. And I'm sure you all saw that. So the next slide will show the 3 still pictures. This is how the polar field looked like, negative polarity in 2004. And you already see a kind of ring of opposite polarity surrounding it from the mid latitudes. And again, we're looking directly down to the South Pole. And then in nine years later, you can see how that field almost disappeared. And you still have very diffuse opposite polarity field around. And then 4 more years, and you see that the positive polarity field now rebuilt in the pole. So because of the observations are noisy and because we have very strong projection effect, I mean, you can see that the radial structure towards the pole, it's not because of the polar field is like this, it's because of that, single pixel in a sky image actually takes, a very large fraction of that. So it's a projection effect. But from this evolution, what you see is that the most changes in the polar fields are not because we have new flux emergence somehow develops, but because of the fluxes transport from low latitudes to high latitudes. And the most of evolution in the pole is because of that flux transport, which suggests that we can model polar field quite well using the flux transport models. And just some basic description of surface flux transport model. We start from describing the radial component of magnetic field as a function of co-latitude, azimuth or longitude, and time. And radial field is, in this case, can be represented by two vector potentials, poloidal, toroidal components of vector potentials. There is additional term that we introduced to this equation, and I'll talk about this in the next slide. But this term describes magnetic field decay, and on the next slide I'll explain why we introduced that. So then, what you do, you can evolve these two vector potentials using known processes in solar atmosphere. So it's a differential rotation. That's the component. Meridional flow. And then there is a superground diffusion that enters both vector potentials. And then there are source terms. That's the new active regions emergence. This component comes from magnetograms, and differential rotation, meridional flow, and superground diffusion are modeled using some parameters. And you can see the expression for differential rotation, expression for meridional flow. That's what typically people use for the surface flux transport models. So we have to introduce additional term, magnetic field decay. And it's easy to understand if you kind of in a hand waving fashion. So what differential rotation does is basically shears magnetic field, right? So equatorial part rotates faster than higher latitudes, and so you introduce the shear. Meridional flow transports magnetic field from low latitudes to high latitudes, away from equator towards the poles. And supergranular diffusion basically spreads magnetic field away from the concentration of magnetic field active regions. In the source terms just introduce new active regions when they emerge. So what happens as a result of this, you're transporting magnetic field towards the poles, and when new active regions start emerging, because of the polarity reversal for the new cycle, new active regions, the magnetic field that is transported to high latitudes is opposite polarity to existing flux in the poles, and that flux interacts with each other to cancel out, and that allows reducing polar field and rebuilding opposite polarity field. So what happens if there are no active regions emergence? And that's happened in cycle 24. For a long time, we didn't have any new flux emerge, new active regions. And the surface flux transport models were not able to reverse the polarity of the polar field because, again, given those mechanisms, what happens in the pole. You have unipolar field, and supergranular diffusion spreads this field around. Meridional flow brings it back to the pole. And so there is no mechanism to dissipate magnetic field if there is no new flux emergence. So to deal with that, we basically introduced that magnetic field decay term. So magnetic field, even if in absence of new flux emergence, over the time that magnetic field will be gradually decaying. So that's the only reason for introducing this. So now we have the surface flux transport model, and just to give you an example how well it works, this is this example of applying surface flux transport model to observations from 1975 through 2019. So we used multiple magnetographs data, and this example of NSO kit peak observations for that period. And I think at the end, it also includes Solace. So you can see how well that surface flux transport model actually can replicate observations, right? And again, what we get from the observations are strong fields from active regions only. And whatever you see in the high latitudes and polar regions is all created as a result of that flux transport. So modeling polar fields was done before, and it's done as part of the Air Force data assimilative photospheric flux transport model, ADAPT. And so again, the same mechanism, same model, except for the decay term that we introduced. And you can see that in the polar fields, you do see magnetic fields in the poles that are kind of created by this ADAPT model. ADAPT also try introducing far side active regions from far side imaging. And here's an example of that when without additional active region of far side, you can see that I think it's AASA and Lille model predicts that there is a small coronal hole. You can see that white contours in this inside of the big red circle. And one of this is a coronal hole that predicted by ADAPT, and it's not there. But after ADAPT added, active region based on a far side imaging, that coronal hole disappeared. However, what we did in this work, we asked a different question. We, for far side imaging, and here's an example from GONC data, you can see very strong signature of far side, active regions on far side for strong active regions. So you can see this very, bright reddish color or yellowish color signature of far side active region. And in fact, when this area rotated to the near side, you would see well-developed active region there. You also can see signature of active regions that were present on a near side and then kind of decaying on the far side. But how about, and that was a question for this study, how about the active regions that kind of small flux, short-lived active regions, the active regions that emerge and disappear on the far side? So we never see any indication of them on a near side, not before, not after. And that's kind of essence of this work. That's what we did. So we took observations from, mostly from NSO, and there is NSO kit peak magnetograms, I think 3 different instruments, and then Solace, VSM continued the data set through October 2017. And then we added to this data set, kind of continue after October 2017, we continued using SDO-HMI data. This data set for this particular study was used through April 2019. And we use both synoptic maps and full disk magnetograms. So for synoptic maps, well, we use both of them to identify active regions. but we use them slightly differently. So the question we ask is really related to lifetime of active regions. So how the effect of small flux, short-lived active regions, what effect they have on the polar fields. And for that, we need to determine lifetime. So we used full disk magnetograms first, and we identify active regions based on a flux threshold and the connectivity of pixels. And then we looked at and track these regions, and that's what shows the red color here. You can see that the regions we identified as active regions, and there were different fluxes, weaker fluxes, stronger fluxes. You can see the distribution, that there is a large fraction of this kind of smaller flux bipoles that live few days, and then the number drops, and then you see active regions that live longer. However, looking at the full disk images has a limit for active regions only crossing the solar disk. We don't see if the regions continue exist, on the far side. And so you can see that these red dots, those are based on full disk magnetograms, really end about 10 days or 12 days. That's because, well, active regions, that's the time active regions cross the solar disk. So to continue to determine the lifetime of active regions beyond that, we use surface flux transport model itself. And so what we did, we would start from active region that is observed on the front side, and we continue evolving it for a number of days. And then we, at the end of each day meaning not computing time, but lifetime of active region in terms of time. And then we would stop simulations, and we see if we can still identify active region using the flux threshold and other parameters that we kind of set up as a definition of active region. And so by doing this, we were allowed to, we were able to actually trace the active regions as they decay for 40 days or so. And you can see blue dots. That's what we get from these simulations, basically evolving real active regions through flux transport, and see when the code will stop identifying them as active regions. And you can see that these blue dots and red dots again, real observations. Blue are this determination of lifetime based on the flux transport. So you can see that they actually behave very similar. Distributions are very similar. Both in histograms are similar, and the distribution of this lifetime as a function of magnetic flux also quite similar. And so for the next steps, we use this lifetimes that we determined from simulations from the flux transport. Although, as I said, we used real observations to verify this early part. All right, and so now we have this set of active regions with their lifetimes for 3 cycles. Actually, 4 cycles, not 3 cycles. And just to demonstrate, how well we for those active regions that we identify, we actually classified them by their polarity, by their latitude, that they belong to a particular wing of activity in either northern or southern hemisphere. And you can see how, by colors, you can see that we actually separate them quite well between these wings. And the reason we did that, then we combine all of these wings and treated them as a data set of kind of evolution of solar activity over cycle. So all of this were combined in a single cycle, basically from the beginning to end. And that's what is shown here. Those are properties of our active regions that we identify as persisted or lived for 7 days. So only short-lived active regions are shown here. And you can see the typical flux distribution. So they're not extremely small. If you compare it with 1 Chile, this plot of magnetic flux and polarity separation. So we're talking about 10 to the 21 Maxwell flux, and so we're somewhere in that area, in a kind of low part of this distribution of active regions. So not very strong, but relatively small. And you can see the separation. Typical separation is about 1 degree or even less. And I'll explain what these two lines means in a second. And so if I take a typical flux on 10 to the 21 Maxwell and typical separation about less than 1 degree, that's where we are on this distribution. So that's the active regions we are looking at. Smaller flux and smaller in separation. So the magnetic fluxes are shown here, and on the right side you can see color and lines that corresponds to cycle, what cycle number, 21, 22, etc., and which hemisphere, northern or southern hemisphere. So fluxes are about the same behavior. So you can see that at the beginning of cycle and at the end of cycle, this is about 11 years or 12 years. That's the cycle. All this data go to a single plot, right, like this. And so at the beginning and at the end, there is a very few active regions, and so there are lots of scatter in this sense. But in the middle part, there is enough active regions to average, and that's what we see in the distribution of fluxes. Then separation is what is plotted is really one standard deviation limits in a latitude separation, or latitude, longitude, or total separation. And the mean value, the center of the distribution, somewhere in between of those. So it's about 1 degree maybe in this case. And this is a plus sigma minus sigma ranges, right? That's what is shown. The same for the separations and longitude, latitude. And what I see here is that distributions don't change that much. So for different phases of cycle, the distribution of these regions, that short-lived regions, are more or less stable. So it's about the same mean and about the same standard deviation, right? Now we use this subset of data for these active regions that actually lived for 7 days, and we use other subset that lived only 4 days. But we use this as a seed for our simulation. So we run surface flux transport model regularly, and then we insert active regions from that subset, that short-lived small flux active regions on the far side of the sun. We insert them only at the central meridian, and we base this insertion on the presence of active regions on the front side. So, for example, if we had active region of non-Hale polarity on the front side, we would insert non-Hale polarity on the far side, or other way around. And then we continue running this sort of transport model and look at the polar fields. So here's kind of summary of super synoptic map that shows on the upper panel. This is synoptic map showing the evolution of magnetic field with this additional far side flux and the 7-day kind of lifetime small active regions inserted. And on the low panel is the same surface transport model simulation, but without added far side flux. And you can see that in mid latitudes it's the same. There is very little difference there is no difference in polar surges. There are some exceptions when there are some differences, like looking on this place, for example. You see that appears that this particular polar surge got stronger when we inserted additional short-lived active regions on the far side. But in most other cases, we don't see any change in polar surges. But the polar fields are definitely stronger. So you can look at this, the intensity in the South Pole, and it's definitely stronger with additional far side flux inserted, and the same for negative polarity And so there is effect of this far side flux added. And the question is how big that effect. And so here's the polar flux. And polar flux was determined for all flux above 60 degrees latitude. And in this particular case, what is shown, these dots are observations. So red dots and blue dots show a different polarity magnetic field, and you can see the polar field variation and reversals. Then this is from observations. Then dashed line shows the polar field as determined from the surface flux transport model without far side flux added. And the solid lines, and we did number of realization, not single realization, but in this case it's, we show 5 realizations with additional small short-lived active regions inserted in the far side. And you can see that if we add this magnetic flux from small active regions that are not really surviving more than 4 days, right? So this region, by the time these regions rotate to the near side of the sun, we don't see any indication of them. So they disperse to the point of they're not identified as active regions anymore, even as a remnants of active regions. But you can see that even adding those regions that live only 4 days, we do improve an agreement between observed magnetic field in a polar areas and this simulated by surface flux transport model. Then if you do this for 7-day regions, so regions that live longer than 4 days, for up to 7 days, then you can see, and I can switch between 2 images. You can see that agreement with observations are actually improved. So we see better agreement if you add these regions that live a little bit longer. And 7 days is about maximum as we decided to use, because 7 days, since we insert active regions at the central meridian and the far side of the sun, 7 days is about the time those regions will start appearing in a limb. So we don't want to consider regions that we still can see in the front side, right? So that's the reason for 7 days. So again, just flipping between of them, you can see that there is improvement. And we did other tests, the statistical tests that indicate that we do see, improvement, notable improvement in polar field representation if we insert these regions that are short-lived active regions. So this is a short presentation. Hopefully get some questions. So in a summary, it's from this exercise, it's clear that fast-started solar activity is really essential for understanding the long-term evolution of polar fields. There were several recent studies that, again, using surface flux transport models that suggest that dipole moment of the sun is really determined by very few small number of active regions. So the dipolar moment is determined by large long-lived active regions, to a very large extent. But what we show here is that the small short-lived active regions cannot be neglected. They're still important, even if you don't see signature of them, in the nearer side. They still contribute to polar field in kind of longer term. When we add these regions, it improves the polar field representation. And the way it improves, we see the increase in strength of polar field. And we also see a slight delay in the polar field reversals, which actually fits better of observations. And the delay is not significant, it's several months, but it does move in the right direction, indicating that, well, this is important ingredient of this. As I said earlier, we don't see a clear indication of any poleward surges that originates or related to this short-lived active regions. But instead, what we see is this continuous, weak flow of magnetic flux, not well organized, and it does affect polar fields, but in kind of longer term. And I'm doing that time. I think I'll stop here. Thank you. And if there are any questions, I'll be glad to answer. Thank you.
Questions? If you have questions, you can just jump in directly or raise your hand.
And Todd, you should be able to unmute and talk. So if you can't, let me know.
I think I can. Thank you. So Alex, can I summarize? And so it sounds like you've come up with sort of a statistical distribution of typical active regions that last for 4 to 7 days or whatever time period you wanted to do for that simulation.
Yep.
And then you've added them in on the far side and found a difference in the polar field.
Yeah.
So does that mean that a typical active region contributes a certain amount to the next cycle's polar field?
Yeah.
You could probably come up with a number of a dipole moment.
Yeah.
And I guess that would be consistent with what you observe on the front side ones. So
right. So this short-lived active regions, they exist on a front side as well, and so they are counted on the front side because every time you identify active region, you add it to the list of active regions, and they add to the flux transport simulation. But those that are on the far side, you don't see them, but they still exist. They still emerge and disappear. And you're right in a summary that we created a distribution of these regions, and then we inserted them in the far side. And there is a measurable, notable effect to dipole moment from these regions when we add that. So I think it's possible to quantify the effect, maybe in simple terms. How much dipole moment you will expect from strong regions and those short-lived active regions, at least in a kind of statistical way.
Yeah, I think this is a really interesting analysis, and I look forward to even learning more about it. I had another question about the meridional flow, and my memory was that the meridional flow was one of the parameters that you could tune to match the polar field strength for each cycle. Right. And it suggests now that maybe that meridional flow value was either wrong or different if you include more active regions from the far side. So have you looked at yet any of the differences that it might mean for the parameters of the model, whether it's the diffusion parameters or the meridional flow or something else?
Yeah, not on this project. We didn't look at that yet. If we, how much we can reduce the meridional flow if we, add this new, additional flux on the far side. As part of this, I mean, it's that developing and working with this flux transport model. There were several papers and several studies kind of related to this, and as part of this, one of the studies was to look at robustness, right? So you're right, in a surface flux transport, you can tune all of these parameters. So you can tune, choose a different superground diffusion coefficient, and that would affect how the model behaves. You can change the meridional flow speed, and that also will change. And so the study that we did, early study, was to look at how robust the the results of flux transport model if you vary these parameters. So it was a study with basically a matrix of different values for all of these parameters. And it turned out that flux transport model is very robust. So if you're not crazy about one of these parameters, so if you're not going off limb on a diffusion coefficient, it produces very similar results. So there is this robustness in, even if you change each parameter, they still produce very similar at the end, very similar results. But we didn't look at this. If you add, what would happen if you add additional flux on the far side? Would it allow you to, say, reduce the meridional flow speed? That wasn't looked at yet.
Thanks.
Alexei, I have a question too. It's from what you say, it seems that the assumption is that all the flux in the polar caps come from active regions.
Right.
And the question I have is how much extra flux might be coming from the background field versus that from the active regions.
Yeah, I mean that's the nature of flux transport. So all flux is assumed to come from active regions. So there is no other flux. That's the nature of the model. You're right that it could be some other sources of active the magnetic flux, right? But that's how the model treats them. Everything is from active regions, not from any other sources.
Yeah. If you look at coronal holes, quite often they are connected to the polar caps. So the old idea was that they were extensions of the polar cap. That is, of course, wrong. Coronal holes that are linked to the polar cap, they're really flux moving towards the pole, not away from the pole. But it seems that you then also assume that the flux in the coronal holes come only from active regions.
Yeah. And there is some, I think there is some truth into this. We looked at several years ago was a study looking at the formation of isolated coronal holes on the remnants of active region. And so we did find, well, the idea was that you're looking at you're starting from, bipolar magnetic field. That's what active region, fluxes are perfectly balanced. But at the same time, observationally, we know that the leading polarity field in sunspot is more compact, stronger magnetic flux, and the following polarity is more dispersed. And so from that simple kind of observations, you can assume that, well, if you apply the same dissipation mechanisms to both, one polarity should dissipate faster than other, right? If one is more dispersed, it's going to last less than other polarity. And so we did find examples when active regions, simple bipolar active regions evolved, and over several rotations, it was an isolated coronal hole formed in one of the polarities of that active region, right? So, and then for some of them, we found that the new connections were formed with polar coronal holes. And so, I don't know, those are anecdotal examples maybe, but I think there is a complicated picture of evolving magnetic field that we might not fully understand or interpret in some simplistic way.
Yeah.
That so
okay.
I don't know.
Yeah, thanks. The one last thing, during the Maunder minimum, when there were, let's say, very few, if any, active regions, how would one explain that the polar caps probably still had enough flux to modulate the cosmic rays?
Yeah.
And that's another issue here.
Yeah. So we did again the flux transport model has a lots of potential to study all these scenarios, right? And so what we did in one of the studies, we limited active sunspot activity to only to one hemisphere. right? And its observations actually indicate that during the Maunder minimum, sunspot activity maybe was limited to one hemisphere. And then what we found is that there is some flux that actually can cross solar equator, and even if you have activity in one hemisphere, you still form solar dipole. So each pole will have, opposite polarities. It takes longer, and that's when we found that we need to introduce that decay term, because otherwise it would not be physical. But yeah, it's possible that even during the Maunder minimum, if you have limited activity in one hemisphere, you still need some active regions. You cannot have no active regions at all. It could be active regions or small bipoles that are not detected as sunspots. You may not see them. Magnetic fields may still be there. But in principle, those experiments with flux transport suggest that you can still create dipolar field, and it will decay. It will not last indefinitely because it will decay with time, but it lasts long enough to be, I guess, to have impact on a cosmic rays probably.
Yeah. Okay. Well, there's still a lot of things to do. Huh? So.
Absolutely.
Yeah. Thank you.
Thanks.
I think Lisa had her hand raised. Lisa, do you still have a question?
Yeah, sure. So I'm trying to think back to your plots, and I remember seeing your plots about the separation distance, but I just can't recall what you said about the active region tilt. Did you say that you were just using the standard Joy's law tilt? What kind of distribution about that active region tilt you were using? Did you vary those parameters at all?
No, it's let me just share it, that particular slide. Oh, sorry, pressing too many buttons at the same time. No, since we determined for each active region that we identified, for each of this region we determined polarities, right? So we found leading and following polarity.
Mm-hmm.
And so based on this, we were able to identify the separation latitude and longitude.
Okay.
But we also, I mean, we had data that allow us to insert the correct tilt, right? So we didn't use any distribution of tilts. Tilts are from this distribution of active, actual active regions, right?
Okay, and then the latitudinal and or the longitudinal separations, the separation distance, did it have any variability with the strength of the magnetic flux? So, for instance, a smaller active region, you would expect to have a smaller separation distance as opposed to a larger active region, or is it just constant across the board?
No. So basically we created these distributions. So this is all active regions that we have, just turning on the pointer. So we have all these distributions, right? And they have scatter.
Yeah.
What we show here is a mean values of flux, right?
Sure.
And they all plotted on this, 0 to 12. So it's one cycle, right?
Yeah.
So now when we did modeling for, let's say, for year 1 of solar cycle, for year 5, we would go and take random selection from this year, for this year of cycle, of that flux, and whatever happened for that flux, whatever happened as a separation tilt angle, we will use it. So it's basically a large data set of this active regions, and we just randomly select them from that distribution, but we selected 4 specific phase of cycle, right? So as we model, so the activity goes and you go from high latitude at the beginning of cycle.
Sure.
Then the selection will be made from this part, right?
Okay.
When you're in the middle part, kind of that, then the selection will be somewhere here, right? And when you're down here, then it will be from this part. So that's how it was done.
Okay, so you're just using these
Yeah.
these mean, these averages, and some kind of distribution. So there is a little bit
Yeah.
of variability from these distributions.
Yeah. Yes.
Now, what about in terms of, so you've got your latitudinal and longitudinal distributions as separate values. What about the tilt as a function of latitude? So if you're just pulling in from these.
Yeah. Whatever happened for this phase of cycle, right? And again, since we know the leading and falling polarity,
I see.
that will be the tilt angle
I see.
will be used, right?
Gotcha.
Yeah.
Okay. All right. Thank you.
Thank you.
So Alexei, did you put in anti-hail regions? I noticed that you have some negative longitude separations there.
We did, yeah, we did. It was a little bit artificial in the sense that this insertion of flux on the far side was really tied to the flux on the front side. So if you see non-hail polarity region on the front side, we will insert non-hail polarity on the far side.
Okay.
So I mean, a little bit artificial, but it gives you the same fraction of hail non-hail as you actually observe. So it's not based on any statistics. It's just if you see it, well, that's what you have on the far side as well.
Yeah. So there's some time correlation. So you're sort of doubling the effect. But yeah. Okay. I get it.
Yeah.
Nice. Okay. Really good. Great work.
Thank you.
Phil, you have a question?
Yeah. So you're putting in the far side flux at sort of random Carrington longitudes, right?
Right. Well, we did it on the central meridian and the far side, right? So it is
so,
random. Yeah.
As days go by, you're spreading it in longitude.
Yeah.
Carrington longitude, solar longitude. So that's what would structure the larger scale patterns, the UMRs, and places where you can have coronal holes and so forth. So I wonder if preserving that, I mean, that large scale structure was shown 30 or so years ago, that you can recreate it by putting in just the largest regions, which of course live long enough so they're on both sides.
Yeah.
So I'm wondering if you put in how much do you disperse or diffuse the large scale patterns? Have you looked at individual rotation plots to see how they look, or just the super small charts?
No, we have this by synoptic map. So we have that each simulation on a kind of synoptic map scale. So we do see how the active regions disperse. If there is large active region that emerge in the far side, it's likely will survive, and so it will be included when it's on the near side anyway. So we didn't really look. We didn't try to insert those, but because they are added to simulation later when they are on a near side. But that adds some uncertainty to the modeling, because you insert in these regions, large active regions, maybe not the time when they have a maximum flux, maybe later. So they already start evolving. Again, this is the nature of that model, that that's how we do it. Yeah.
Yeah, because the sun doesn't treat all longitudes the same.
Yeah.
As has been evident for the past few days, when the Earth side of the sun is empty.
Yeah.
So that is not, it doesn't have symmetry there.
Yeah.
So curious to see how putting in the larger regions on the far side might help to, and just leave the small ones to be, they're adding flux at the poles, but they don't add, they probably don't contribute that much to the large scale pattern.
Yeah.
But,
Yeah, the way I see this type of kind of experiments is really to provide a justification for having, observation of sun from more than one place on an ecliptic, right? Or maybe even, from the poles. So it just I think adds to this argument that we need these observations from multiple viewing points, not just from even if we can somehow improve the agreement, right? It's better if we have these observations to begin with. So I don't know. That's one of the goals of this, that demonstrate that, well, we do need distributed spacecraft along the ecliptic.
I don't think you need to convince any of us about that.
Yeah.
Well, Shay and Reiju and Junwei have a list of far side active regions based on what they've learned from the AIA data since 2010 or so, I guess, and could probably provide you with a list. It might be interesting to look at that and pick the ones that are smaller than whatever and use that as a seed just to see how that works, to see if it would, because I would think it would improve the fidelity, but you never know.
Yeah. No, it should. And maybe related to this, as part of the experiments that we did, that I mentioned earlier, we also looked at how sensitive the result of flux transport to actual distribution of magnetic field. So you have leading polarity and following polarity, and they in a magnetogram they have this irregular form, right, a shape. And so we looked at this saying, well, if we preserve fluxes, if we preserve tilt angle, but we replace actual flux distribution by a circle with the same flux, same central latitude, how that would affect flux transport model. And the conclusion was that it's not sensitive to much. So it's still very robust. So that's actually very applicable to far side, because you don't really know what where the leading polarity ends and when the following polarity starts. But you know the size, approximate flux, and so if you divide it by into halves and say, well, that's my flux, total flux, and you just put two Gaussian circles as leading flux and following flux. The experiments that we did suggest that it will be sufficiently good for flux transport model. So it should give you a very similar outcome if you had the actual distribution of magnetic fluxes. So no, we should try that. Absolutely.
Mark DeRosa has had his hand up.
Hello.
Mark?
Quick question. So first of all, I joined late. Sorry if you discussed this already, but I was sort of wondering, you talk about adding active regions that last for a certain lifetime. And that's typically not what I think of when for example, when you add active regions to the model, you just sort of drop them in and then you let the model dynamics take care of its evolution from then on. So how do you know that you're dropping in an active region that's going to last for 4 days or for 7 days?
Yeah.
Is there a correlation? I guess there might be a correlation between certain properties of the region you're inserting and its eventual lifetime.
Yeah. So I don't know if you missed this. Let's see this. Let me share that screen again. So what we did, we selected, we used the front side observations to let's see, it takes some time. Yeah, so we use the front side magnetograms to look at the lifetime of active regions, but then we also model lifetime by basically applying surface transport model to each active region that we identified in the front side, and we look how long it will last, right? And so those that we observe on the front side, this red color, and those that we model in a blue color, obviously in the front side you only see them for 10 days, 14 days or so, and then they rotate. But from modeling, you see them, kind of lifetime continue. And this was done until active regions are not identified anymore based on the criteria that we imposed, flux threshold and other things. And so that's where the lifetime comes from. So basically, we determine the lifetime from this and say, well, this is our distribution of active regions, right? And this is active regions that we identify that actually live that long, for 7 days, right? So we only insert those regions that are satisfying this requirement. So we're not inserting regions that live longer according to this kind of distribution, right? And the reason is that we really want to see the effect of regions that emerge and disappear on the far side before we see them on the front side, right? So if you see them on the front side, then well, we know that it was an active region, and it's already taken into account later in the flux transport. But if you don't see any indication of regions that emerge and disappear, then the question was, well, how big the effect is? And that was the kind of goal of this study, looking at these particular regions.
Okay, so you're taking advantage of the correlation between the amount of flux and the statistically averaged lifetime, it sounds like.
Well, I mean, it's those actual active regions from the front side, right? We just kind of classify them, how long they live based on, well, observations and that simulation later for the later times, right? And that's our seed distribution that we use to insert these regions on the far side, right?
Okay, well, it sounds to me, I mean, like, I guess I would have framed it as inserting active regions with a particular amount of flux or something, rather than, because you don't really, I mean, because like the lifetime of a particular active region also depends on the other stuff around it.
Sure.
So you can't, I mean, I understand what you're getting at. You're trying to account for flux that emerge and dissipates into the background all during the time that the sun is, like while those longitudes are on the backside.
Yeah.
But it might serve to answer one of Life's questions earlier, is that, like, if these sort of smaller flux regions that don't develop sunspots, for example, are constantly emerging and dispersing, it might help to explain why there's still dipole reversals during Maunder minima when there's no obvious sunspots, no evident sunspots.
Yeah.
Anyway, thanks for the talk.
Thank you.
Okay, it's been an hour. We have a very great discussions and questions. So if there's no more question, okay. Last round, no more question. Okay, if there's no more question, let's thanks to Alexei again. Very wonderful talk. And thank you for giving this wonderful talk to COFFIES. And again, the recording of this talk will be put online at COFFIES website soon after this talk. And anyone, if you are late or if you can't attend, but I guess those are not here right now. So anyone will be able to watch the recording on the COFFIES website, which is coffees.stanford.edu later. Okay. So thanks to Alexei again, and
thank you.
Bye-bye.
Thank you all.
Thanks, Alexei.
Thank you. Bye.
Bye-bye.